Okay, so far in your mathematics career, you have mostly worked with two-dimensional shapes. You probably know what two-dimensional means, right? You've seen 3D movies. You talk about 2D video games all the time. You probably know what it is, but what is a two-dimensional shape? Well, a two-dimensional shape is just a shape that is sort of flat, right? It can only exist on a piece of paper. You can't build one with wood, right? A 2D shape is totally flat and it only has two dimensions, right? It goes up this way and up this way, right? We know a lot about 2D shapes. We know how to name them. We know that this is a square, right? Or a rectangle. We know what a triangle looks like, right? We know what a circle looks like. We know all of these two-dimensional shapes. We feel very confident about those, I'm sure. In the last sort of unit, I suppose, that you worked on, you found the area of two-dimensional shapes, of composite two-dimensional shapes, things that didn't have, nice simple names like rectangles, but were rather, had weirdo, bizarro shapes, right, like this. You worked with these and you feel pretty good about them, I think, at this point. Well, now we're going to be expanding that into the territory of three-dimensional shapes. And what do I mean by a three-dimensional shape? Well, it's sort of difficult to express what a three-dimensional shape is on a screen like this, right? You're watching this probably on a laptop somewhere, and the laptop can only truly show two-dimensional objects. It's a flat screen. But we can get a rough understanding of what a three-dimensional object is by doing some sort of tricks with drawings, right? So here is a three-dimensional shape, right? It is a shape that has multiple dimensions. Not only does it have this flat front, but it also goes back and sort of sticks out into the third dimension, right? 3D shapes come in all different shapes and sizes, and naming them can get pretty complicated pretty quickly. But there are some that you need to know, and we're going to talk about those to begin. So when we're constructing a 3D shape, we can start with a two-dimensional base, right? So here we have let's make a rectangle to start. Here we have a rectangle, right? Kind of. Let me try to make it a little nicer. That looks a little better. Here we have a rectangle, right? This is going to act as our base. I'm going to highlight this to show that this is our base. And then with this base, we can sort of stretch it out into the third dimension, right? So I'm going to sort of stretch it out, and now it's going back into three dimensions, right? What do we call this three-dimensional shape? Well, because it started off as a rectangle, the base was a rectangle, we call this a rectangular. We call this three-dimensional shape a rectangular. What sort of rectangular? This is called a rectangular prism. Because we took a rectangle and we just sort of stretched it and made it go into the three dimensions in each direction like that, right? It started off as 2D and we just sort of brought it back and made it 3D, right? So this is called a rectangular prism. Similarly, if I start off with a triangle, something that looks maybe like this, right? We start off with a triangular base, right? This is a triangle. This is our base. Our triangular base, if we stretch it out, we are left with a triangular prism, right? Anytime that we sort of take a standard 2D shape and stretch it into the third dimension this way, we end up with just a prism of that shape. So we had a triangle, we stretched it out into three dimensions, so we ended up with a triangular prism. And this works with any sort of shape you can imagine, right? You want an octagonal prism, just draw an octagon and stretch it out into three dimensions like this. Maybe it's got a little bit of a side there, and we can even draw these dotted sides as well. These dotted sides indicate sides that we can't really see, but we know that they exist on the other side, the parts we can't see. Okay, so that's not the best drawing in the world, but it's decent enough. And we can sort of get that. And this would be an octagon, right? So an octagon, but it's an octagonal prism. Okay, so that's the first key type of 3D shape that you need to know, right? There are infinitely many types of prisms, right? A dodecagon, right? That's a 12-sided shape. A dodecagonal prism is going to be a 12-sided prism, right? Or a dodecagon sort of stretched into the third dimension to form a prism. Any shape you can imagine, you can do that with, right? So here are some, you can ignore these for now. Here are some of those prisms, right? Maybe drawn a little bit better though, right? So we can see we have the triangular prism, right? It starts off as a triangle and then it's stretched into the third dimension. The rectangular prism starts off as a rectangle and it's stretched into the third dimension, right? Whatever you want, you can make in that way. But what are these over here? Well, let's talk about it. So we can start off with, again, with a similar base. I'm going to draw a square. This is a square, right? Roughly. It's maybe a little bit more of a rectangle. But rather than just stretching back straight into a square prism, we can instead come to a point. If all the sides, rather than going straight back, they all go straight to one point, that gives us what is called a square, because we started off with a square. We have a square base. But rather than a square prism, let's try spelling again. Square. Right? Rather than a square prism, we get a square pyramid. Right? You've probably heard of the pyramids of Giza, right? The Great Pyramids, one of the last ancient wonders of the world, right? The pyramids are very similar to the prisms, but rather than going straight up and maintaining the same shape throughout, they come to a sharp point, right? So let's go back here and we can see better drawings than what I can make, right? So we start off with a square down here, but rather than going straight up and making a prism, right, like that, all the sides, they come to a sharp point. Here we have a triangle base, and they all come to a point, so this becomes a triangular pyramid. Here we have a pentagon as a base, right? This is a 5-sided base, a pentagon, but then all those points, they come to a sharp point like this, giving us a pentagonal pyramid. Hexagonal pyramid. There are infinitely many different types of pyramids you can make, right, for any type of shape you can draw, any 2D shape. So that's sort of the naming scheme that you need to know when it comes to 3D shapes. Now, there's all sorts of different types of 3D shapes. These don't encompass all the shapes, right? A ball is a sphere. You might have heard about that before. We'll talk more about those in 7th grade. Sort of hard to draw, but you have spheres, you have cylinders, right? Those are circles turned into prisms. You have tetrahedrons, which is another name for the triangular prism pyramid. A specific type of triangular pyramid. There's all sorts of different 3D shapes, but these are the ones you need to be familiar with for now in 6th grade. There's also the cube, which is a special type of rectangular prism where each face is a square of the equal dimensions, right? So a cube, you've seen a cube, right? You can think of a dice, a Rubik's Cube, those sorts of things. But if this side length was 10, we could also expect this one to be 10, 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 this one to be 10. All of them would be 10, and that's a special 3D shape. It gets a special name because all the side lengths are the same, and it's a pretty important shape. So that's a cube. Okay, so for your first homework, I want you to try drawing the following shapes. Now, drawing these can be pretty difficult. Our brains aren't immediately the best at sort of translating these 3D shapes onto 2D paper. But maybe, pull up a picture on your Chromebook of what a rectangular prism is, what it looks like, and maybe do your best of copying it down, right? Don't trace it, but try to copy it down. Being able to draw these is a pretty helpful skill. Makes doing your work a lot easier. Makes calculations easier when you have a drawing to work with. All right, so try drawing each of these shapes. I don't expect them to be perfect. I don't expect them to be neat and tidy. Just do your best. So that's homework 1. Draw these 6 shapes. Okay. Note that some of them are prisms, some of them are pyramids, right? What are the difference there, and what's that going to look like on paper? Okay, so Now that we know what these 3D shapes are, let's start taking some notions about 2D shapes and expand upon them into the third dimension. So here we have a 2D shape. We have a rectangle. We can find the area of this rectangle pretty easy. At this point, you're pretty good at this, right? Just 12 times 10, right? So our area is going to be 120, right? Pretty easy with a two-dimensional shape. Well, there are some notions about area that can be sort of taken from 2 dimensions and brought into the third dimension. When we're calculating the area of this 2D shape, we found the area was like 120, maybe we'll call this inches squared. We found this area was 120 inches squared. That tells us some things. Maybe we need to figure out how much paint we need to paint this square. Well, we're going to need 120 square inches of paint. How much cardboard do we need to make up this area? Well, we're going to need 120 square inches. If this was maybe a room, how much carpet would we need, right? The question of area is a very useful one. It's one that's brought up a lot, and it tells us things about it. But just like we might want to know how much, cardboard it takes to make a square like this, well, what if we're making a box, right? What if we're making a 3D shape? How much cardboard do we need to make this 3D shape? Or how much paint do we need to cover this 3D shape? Well, that's where we get to a new concept called surface area. And all the surface area is, let's say this dimension was 10. All the surface area is just the area of all these different faces, right? This front face. Then we've got this part over on the side. We got this part on the top, right? We've also got a couple that we can't see, right? We have a part on the bottom. We've got one coming along the side here. I'll do that in blue, right? And then there's the back that we can't see at this picture, but it's over there and we know it's got to be there, right? Each has an area, right? We calculated this to be 120. We found that area to be 120. Well, the top is 12 by 10, so this has to be 120 as well. The right side is 10 by 10, so this is going to be 10 times 10 is 100, right? So we have all these areas. We have 120, we have 120, we have 100, and then there's some sides that we can't see. But what do we know about these sides, right? If this side over here is 100, well, the other side is probably going to be the same, right? If you're imagining a cardboard box, find any box in your house, right? A box of crackers, whatever. You'll see one side is always identical to the other side when it comes to rectangular prisms. So we know that this one over here also has to be 100, right? We know the back side, if the front side's 120, the back side is going to be 120. If the top is 120, the bottom is going to be 120. So we know we have these areas as well. The surface area of this shape is as simple as taking all the areas, right, all of those 2D faces and adding them all up, right? So here we're going to get, what would that be, 200 plus 680, I believe? And maybe this is square inches. Did I do that right? 240, 480 plus 200, yeah, 680 inches squared. Right, so we found the surface area. In other words, we figured out how much maybe paint it would take to cover this, how much cardboard it would take to build this box. We found the surface area. Okay. Now, the surface area can be for all variety of three-dimensional shapes. So here we have a triangular prism, right? You can find the surface area in just the same way, right? We have a picture sort of color coding it, but we won't find the area of this front triangle. It has a base of 10 and a height of 8.6, so 10 times 8.6 divided by 2, right? We'll get 86 divided by 2, which will be 43. So we can find that this has an area of 43, right? We know the back side is going to be the same. It's also going to have an area of 43. Then we can start working with this side over here. Well, this is 10 by 12, so this has an area of 120. The other side is also going to have an area of 120. Maybe I'll do that in yellow. Right, we go side by side and we calculate the area as we go, right? The bottom is also going to have 120 here because it's 10 by 12 as well, right? So that's 120. As we calculate these areas, right, 120 on the bottom, we had 120 on the side, we had another 120 on the other side, and then the front and back were both 43. We just add all of these up. Make a little bit of room. We add all these up, and the number we get tells us our surface area. So our surface area is going to be equal, in this case, the sum of all these. Well, 120 plus 120 plus 120 is 360, plus 43 plus 43 is going to be 86. So 360 plus 86 is going to be 446, I believe. 446, right? Maybe again, this is perhaps inches squared. That's all the surface area is. Now, conceptually, I don't think it's too difficult to understand, right? It's just all the faces, find all their areas, and add them all up. However, actually accomplishing that task can be more difficult than you would imagine, right? Keeping track of all these numbers, all these multiplications, all these areas, making sure that you actually get every side, making sure that you can recognize what measurements are important for each side, right? When I'm finding the area of this triangle in the front right here, right, I need to know how to find the area of that triangle. I need to work with base times height, which is going to be 10 times 8.6. But not 10 times 10. There's these other numbers here that aren't useful for finding that area. But when I go to this green side, I need to work with different numbers, right? That's 10 times 12 for that rectangle. So you need to be careful. There's a lot of room for error, a lot of room for mistakes, and there's a lot of room to just get lost and confused, okay? So when you're solving these problems, the difficulty is not so much as knowing how to do it, but rather actually just accomplishing the task. I would recommend being very diligent with your note-taking. Show all your work, right? Color code. Those students that are willing to get out their colored pencils often do the best on this. And you'll find that high-level mathematicians often do these sort of same tactics, right? Don't ever be afraid of getting anything out that might help you. Okay, so colors, I would highly recommend to use in solving these surface areas. So for your second homework, I want you to try to find the surface area of these two shapes. Now, if these go well, then great, right? You might be ready to move on. If they're not, you might need to get some further practice. And if that's the case, I can send you some, or your tutor or teachers down there can do the same. Okay. Be careful as well. Again, remember that with these shapes, there are parts of these you can't see in the picture, but you still need to account for with the surface area. With this triangular prism, for example, we have that side and the bottom that we can't see, and we also have that back side we can't see. So be careful as you're going through those. And again, I would recommend color coding as you go, right? When I'm looking at that rectangle, maybe do a green rectangle, and when you find the area, write it off to the side. Okay. Now, surface area is one part, all right? Surface area is one part of the equation. The other component is volume. Volume represents how much can something hold. If you have a box like this, how much can actually fit inside of it? We talk about volume a lot in the day-to-day. Whenever you hold a can of pop, right? You look at the bottom, it'll tell you how much it can hold, right? It'll say probably 12 ounces, something along those lines, right? How do we actually figure that out, though? Now, each shape has its own sort of formula, but when it comes to prisms, we can do a line of thinking that can help us get there. Let's first go back to 2D shapes, and let's think about what we're actually doing when we're finding the area. The area of a 2D shape, let's say this is 2 by 4, is figuring out how many squares, how many 1 by 1 squares can fit inside of this shape, right? That's what we're curious about. So if this has a side length of 2, then it's got 1 and 2, right? It sort of has a break. It can fit 2 going that way. And if this is 4, then it has sort of 4 units that it can fit. Together, they can make, these don't really look like squares, they're not perfectly drawn, but there can be 4 squares along the top and 4 squares along the bottom, right? So together, they have 8 squares. The area is 8 because 8 squares, right? 8 units squared. Each one of these is a square unit because it's square. Volume takes that same idea but brings it into 3 dimensions, right? So rather than how many 1 by 1 squares can we have, we want to know how many 1 by 1 by 1 cubes can we have. So if I have a little cube, right, this is my 1 by 1 by 1, 1 by 1 by 1. How many of these can fit in a bigger box such as this, right? How many of these are going to fit in here? Well, just like with area, we just take this number times this number, right? We have this sort of row of squares. We can fit 2 squares here, and then we can go 4 this way, right? The same idea can be true, but we just need to go account for that last dimension and start making cubes, right? We sort of have a cube there. So we need to multiply by that last dimension. So maybe if this was 3, right, we could fit 3 rows. So here we do the same idea, right? So we take, this was, let's say, 8 going this way, 2 going this way, and 3 going that way. We're just going to take the volume is going to be 8 times 3 to find the area first, and then we just take that area and multiply it by how far back it goes for 2. So 8 times 3 times 2. 8 times 3 is 24, times 2 is 48. The volume is 48. So what that means is that 48 of these 1 by 1 squares can fit inside that box. That's what volume is. That's all it is. Okay? Now, the volume of complicated shapes, you can get as complicated as you want when it comes to prisms. All you need to do, right, if we have a triangle like this, all you need to do is find the area of that first shape and then multiply by how far back it goes. So if we have this prism, and I told you that the front shape's area, this red shaded area, if this had an area of 30, and it went back by 10, then to find the volume of this shape, the volume here is just going to be 30, the area of the triangle. I'll call this the base, right? It is that shape that sort of informed this prism, right? It's a triangular prism, so it's the area of the triangle. And all we do is multiply it by how far back it goes. We call this the depth. So here, our volume would be 300. This would be units cubed, because we want to know how many cubes fit in there. Okay, so all you got to do is find that shape. Now, not all prisms are built the same way, right? This triangular prism sort of goes upward rather than down. But again, we just find the area here. We'll find the area at the bottom and then go up, right? So maybe this area is 30, right? And then we go up from there. So a triangular prism, maybe of these dimensions, maybe we can have a base of 10 and a height of 4 and then a depth of 11, right? We're going to start by finding the area of the triangle, right? So we'll take base times height. So this area is going to be equal to base times height divided by 2, 10 times 4 divided by 2, which is equal to 40 over 2, which is equal to 20. So we know that this red area is 20. So to find the volume, we're going to take 20 times the depth, right? Times this 11 here. Right, so we're going to take that 20 times 11, and that will give us our answer. So we'll get 220 units cubed. So for homework 3, I want you to try and find the volume. You might notice that these are the exact same shapes as the surface area shape, but now we're calculating something different. We're not trying to find the surface area anymore. We're trying to find the volume. The surface area tells me how many squares covers the outside, how many 1 by 1 squares covers the outside of the shape, right? How much paint, right? The volume is how much fits inside of the shape, how many cubes fit inside the shape. So again, do your best on calculating these volumes. If you find that you're struggling a little bit, even if you get to the answer here, it might be a worthwhile pursuit in doing a few more of these. Okay, so that sort of wraps up the 3D shape unit. Right? Now we're going to move on to some statistics. So this is a whole different thing. You know, we're changing our mindsets. We're working with some totally different element of math, putting all the shape stuff aside for now. Data. Okay, we're moving into our statistics unit, and we're going to start off by talking about data. What is data? Well, data is really just a collection of facts about various things taken together sort of to look at all together. So here I have a bunch of flowers drawn. It's just the same flower, copy and paste it over and over. We can collect data about this flower, about these flowers. First, you might notice their colors. So we could have a list of data. This is just yellow, right? I might say Y for yellow, red, blue, red, blue, green, red, red. We collected some data. This list here, this is our data, right? It is just a list of facts, right? This is called categorical data. We won't work much with categorical data, but it's a category. Each flower fits in one of these categories, right? But there's other types of data. Maybe rather than rather than focusing on the colors, we're going to focus on the height. Perhaps this is 4 inches. Maybe this is 6 inches tall. Maybe this is 5 inches tall. This one we'll maybe call 3. How about 2? And then 4, 4, and 4. Right? And these are all inches. This would become numerical data. And that's what we're going to be focusing on in this class mostly. Numerical data, it's numerical because there's a number involved. We want to know something about these flowers, and that thing that we want to know can be represented with a number. Right? So we have a list of data here, right? We have a sort of a collection of data. We're going to work with that data. And the first thing we want to learn is how we can help visualize that data with a dot plot. And that's what we're looking at right here. This is a dot plot. And it goes pretty straightforward on how to actually create this dot plot. Right? First off, we got to give it a label so we know what we're talking about. Height in inches, right? Then we just start plotting our points. We have a 4-inch flower, so we find 4 and we just put a dot above it, right? The next one up is a 6, so we find our 6 and we just put a dot above it. And we keep going, sort of following this pattern, and you don't need to switch colors. You can do all the same color if you wanted. And see, we have a next one was 3, so we put a dot above 3. The next one was 5, so we're going to put a dot above 5. Then we had 4, so we're going to put another dot above 4. Then we had another 4, and then another 4. Right? That's all you do. Right? So here's our dot plot representing our data, and now we can, in one quick glance, look at it and get an idea of what's going on here. We see that most of the flowers are about 4 inches tall. And then there's some shorter and there's some taller. Oh, I forgot to plot my last point for 2. Right. So there's some shorter and there's some taller, but it seems sort of on average they're centered around that 4. Right. So we get an idea of it without having to look at this gross list of numbers and sort of decipher it. We get an instant, we look at it, we visualize it, we understand it. Okay. So that's all a dot plot is. So for homework 4, I want you to try to plot the following data on the dot plot below. I don't think this should be very difficult. Right. You just keep plotting every time you get a new number. Let's say there's no 7s on here, but let's say we had a 7, we put a 7. If we found another 7, we put another one above it, and we keep going, right? However tall we need to go. If there's no data points on that number, that's fine. You just leave it blank, okay? So try this. Yeah, I don't think it should be very difficult. Dot plots are very helpful. They come up a lot, but they aren't universally good, I would say. They don't fit every scenario for visualizing data. So here is an example of some data that wouldn't work good on a dot plot, right? So we can start going 0, 1, 2, 3, 4, right? But you can pretty quickly see the problem here. It's going to take a long time to get to 4 million. My dot plot's going to be huge. Even if I skip count, right? Maybe I'll skip count by 100,000, right? We'll get there. Or even, maybe let's say even by millions. I'll skip count by millions, right? So I create my dot plot, but now I'm going from 0 to 1 million, to 2 million, right? To 3 million, to 4 million. And we create a dot plot, something that looks like this. Maybe spaced out a little bit more evenly, right? But then we sort of lose some of the information here that's helpful, right? We have a dot that's roughly over there by 4 million. We have a 1 on 0. Then we have 346,000. That's like probably, I don't know, really somewhere over there. It's sort of hard to visualize what's happening here. Moreover, if this list of data was longer, we would just get a bunch of dots, and it might not be very useful as far as showing us something about the data. So we can work with another form of visualization called a histogram. This is a histogram, what we're going to be drawing here in just a second. So rather than giving each data point its own plot on the graph, we can sort of clump them together in useful ways, right? What I'll do instead is I'm going to create some intervals. So I'm going to go from 0 to 200,499 or 9,999, something like this. And now I'm going to count how many of those data points I have. 0, 1, 2, 3, 4. I have one data point that fits in that interval, right? 10,000 is between 0 and 249,999. 23 fits in there, 143, 25, and 0. So I have 5 data points that all fit in that section. So what I'm going to do is I'm going to go to this interval and I'm going to sort of create a bar going up, right, to show that we have 5 data points in that interval. Right? My next thing, I'm going to create my next point in the interval. The reason I didn't go all the way up to 250,000 is because my next interval is going to start right at 250,000. And it's going to go to 500,000. Right? My next one, well, there is one data point in 500,000. Right? One data point in 500,000. So I will just put a 1 right there. Now this histogram is going to have to get long to include this 4 million. So for the sake of time, I'm going to cut this 4 million out just so we don't have to make a super huge histogram. Right? But we can keep going with our intervals. Our next interval would be, this would be 499,999. We want each interval to be the same size. So this next one will be 500,000, and it will go to 749,999. And here we have no data points that fit that, so we just leave it blank. That's all a histogram is, right? That's all a histogram is. So with this data here on this homework, I want you to first decide what the intervals are going to be. Decide what the intervals are going to be. I've given you the first interval. It goes from 0 to 999, right? So fill out the rest of this plot. And remember, the intervals need to be the same. They need to be even intervals. Okay, each interval needs to include the same amount of numbers. So I'll give you a hint now. This is going to start at 1,000 and go to 1,999. The rest, I think you can get for yourself. Okay. Now, there are some numbers that we can use to sort of help summarize the data quickly, right? There is the mean, the median, and the mode. And these are all what are called measures of center. If we scroll back to our flowers, right, we notice that most of these center around 4. They sort of center around 4. Now here, if you were to calculate it, you would find that the mean is 4, the mode is 4, and the median is 4. All these numbers sort of point to 4 as the center of the data point, right? Now, each of these try to point to center, but they do them in a different way, and they get slightly different results. The mean, you add them all up, then you divide it by the amount of data. It's sort of the balance center. The median, you arrange from least to greatest and find the middle number. It's just the middle of the data. And then the mode is the number that occurs the most often. And in just a moment, we're going to do examples of all of them. So let's start off with this data set. And rather than start with the mean, so I'll write mean, but let's leave it around for, actually, no, I'm not going to write it all. Let's start with the mode, because I think the mode is the simplest one here. The mode for this data, if I were to ask you, what's the mode for the data? The mode is simply the number that occurs most often. Notice how there are 2 2s here, but there's only 1 1, there's only 1 3, there's only 1 4, there's only 1 5, and there's only 1 100. 2 occurs most often, so our mode in this case is 2. The median is another pretty simple idea. We have 1, 2, 3, 4, 5, 6, 7 data points. So the middle number is right here. It's right in the middle of my data set. Right? There's 3 numbers smaller than it and 3 numbers bigger than it. Right? So our median is 3. It's the number that's right in the middle. Right in the middle. Now, note that my data is already in least to greatest order, right? If my data was out of order, like this, to find the median is not just the middle number in the list. Forgetting a number 3. The median wouldn't be 2 here because we're not in order. We need to first rearrange the data to put it in this nice order in order to find the median. Now, the mean is the weird one. To find the mean of the number, you start off by adding all of the data together. So here I would get 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 4 is 12, plus 5 is 17, plus 100 is 117. So we start off, we do that, we add them all the data points together, and then we divide by how many data points we have. So here I notice that there are 7 data points altogether, so I'm going to take this 117 and divide it by 7, and that gives me my mean. I take 117, divide it by 7. I can do that in a calculator. What I get is 6.88 and so on. 6.88. So my mean is 6.88. And that's what you do for all these. Okay, that's the procedure to find these numbers. And if you notice, 2 and 3 seem sort of in the center of the data, right? They're not, there's a difference there, but 2 shows the most common number. It sort of shows the center. The median sort of shows the center. The mean is a lot bigger than all these numbers, but it is roughly between 1, 2, 3, 4, and 5, and 100. Right? When you factor all those in, it seems like a good fit. Okay, so that's what we're doing here. Oh, I divided by the wrong number. I was thinking this is a little low. I divided by the wrong number in my calculator. Sorry about that. So this should be, if you actually do this correctly, you should get 16.71. Okay, so it's sort of between the 100 and 5. It's another measure of center. Each one comes up at different points. Which one you should use is sort of subjective, but these are some numbers we'll work with more down the line. So for your last homework, or I suppose second to last homework, I want you to calculate the mean, median, mode, and range. Oh, forgot to talk about the range. The last thing that we need to talk about is the range. And the range is pretty easy. Our smallest data point is 1. Our largest data point is 100. How far apart are those two numbers? What is the difference between those two numbers? Well, we can take 100 minus 1. There are 99 numbers between these, so our range is 99. Take the biggest number, subtract the smallest number, that's your range. Okay. So for this following data set, I want you to calculate these following things. Note that the data set's not in order. I would start off by rearranging it and putting it in order from least to greatest and going from there. Okay, there are some special circumstances that you need to account for when you're calculating these. These won't come up in the last data set, but they might come up in future data sets. First off, with the median, what do you do when there is an even amount of data, right? There's no middle number, right? 2 and 6 are both in the middle. What you do when you have this is you find the number that is directly between 2 and 6. And a sort of shortcut way to do that is you can take 2 plus 6 and divide it by 2. 2 plus 6 is 8, divided by 2, you get 4. And 4 is directly between 2 and 6. So the median in this case is equal to 4. Okay? It is the number that is right between those two middle numbers. Again, because we have an even amount of data, we're not going to have one number in the middle. We're going to have two numbers in the middle. All right, so you add them up, divide by 2. That'll tell you the number that lies directly between them. Okay, so our median here is 4. Now, the mode, there are some special cases as well. Let's look down here at this data set. You'll notice that there is a 1, a 1, a 2, a 2, and a 5. No one number sticks out above the rest, right? 1 and 1 are very common, and 2 and 2 are very common. They're both more common than 5, but what's the mode? Is it 1 or is it 2? Well, it's actually both. The mode is 1 and 2. You can have multiple modes for one data set. In a similar manner, when we look at this data set, there is no number that sticks out above the rest, right? They are all as equally common as each other. They're all tied for first, right? So because they're all tied, what we have here is we have no mode. You can write that, just no mode. We don't have a mode. The same is true here. Even though they're both more common, they're all tied for first. So here again, there is no mode. We only have a mode if it's more common, right? If everything's tied for first, then there's no mode, right? So in this first circumstances, we had two numbers tied for first, so there was two modes. But because all of them were tied for first over here, there's no mode. So try with that in mind, calculate these with this following data set. Right? And I think these circumstances should arise, these new circumstances. Okay, I think that's everything. Good luck, Harley. This should last you at least a couple weeks. So we're going to set this for due in 2 weeks. Just get it to me as quick as you can, but try to get it done in the next couple weeks. Okay, thanks bunches. Have a good one.